have a... Okay, so let's continue with hypothesis testing. So yesterday, we talked about what hypothesis testing in general was. So we talked about how initially we had like a mean from a sample, which was 12.68, and then we have our sample standard deviation, 6.83, and then we wanted to know if the population mean was greater than 11. This is what we wanted to find out. This was the hypothesis. Is the population mean greater than 11? And we tried to solve this using the confidence interval, but unfortunately, the confidence interval does not tell us specifically if the population mean is greater than 11. However, the confidence interval tells us the range at which the population, the range that we are confident that the population mean will be in the range, right? Sometimes we get the range right, sometimes we don't get the range right. So it can be conflicting, okay? So, and then I told you guys about hypothesis testing. Basically, you need to have two things or two statements. For the first one is called the null hypothesis, and we denote this as H0. The second one is alternate hypothesis, which is H1. And then we will, from these two hypotheses, we will calculate what is the p-value, and we calculate the p-value using a z-score. I think we haven't gone through that one yet. The p-value will be calculated using the z-score, and then depending on what the value is, we will say that we support, or we say that the null hypothesis is plausible, or we reject the null hypothesis and we say that we support the alternate hypothesis. So we will talk more on this in a bit. Okay, so this is the script if you need to go through this again. Okay, so I have an example over here. We also talked about this one as well. We talked about how we have a sample of 50 modified engines. This is our sample. What are we trying to test here is that this modified design, this modified design will be put into production if its mean emission rate is less than 100 milligram per second. We are trying to find out if our modified design will be emitting less gas versus the original design. So what we're trying to find here is the mu. We're talking about the mean, right? Okay, the mu is less than 100 milligram per second. This is what we want to find out. So a sample of 50 modified engines are built and tested to find out whether this is true or not. So the sample mean is 92, and we have a standard deviation of 21, sample standard deviation. Now, if I did not have this, if I did not have any standard deviation, and I just had the sample mean, the standard deviation was 0, for example, I can certainly say that, oh, the population mean is for sure is less than 100 milligram based on this sample, because there's no standard deviation. My data is not going to be spread out. My data is like confined to one point. But that's not always the case. So whenever I have a standard deviation for my data or for my statistics, I know that this is not 100%. I cannot be confident that this represents the population mean. So I have to find out if this is true or not. Okay. So the keyword here is whenever you have a standard deviation, you will always need to find out whether the population mean is greater or less than 92, or greater or less than the sample mean. Okay, so if there was no uncertainty, then we can be certain and conclude that the modified engine emits less than 100 milligram per second. Since there are uncertainty, therefore we know that the population mean is greater or lower than 92. Okay. Okay, so the manufacturers are concerned that the modified engines might not reduce emissions at all. So they are speculating that actually the new design is just a waste of money. Let's not do it because in reality, it doesn't really reduce anything. So let's not do it. So they are speculating, or they are concerned that the modified engine is not going to reduce any gas. So they said that the mean is going to be greater or equal to 100. So this is their concern. It's not going to be less than 100. Okay, so they want to know if this concern is justified using hypothesis testing. It is possible that the sample of mean could come from a population of mean 100 or more. So if we were to say that this sample mean comes from a mean of, comes from a population mean of 100. So this guy would be over here, right? We don't know yet. We have to find out. So is it possible that our mean can come from this normal distribution? So we're going to find out. So the population mean is actually greater than or equal to 100, and the sample mean is lower than this only because of random variation from the population mean. So this will be our null hypothesis. I'm going to teach you how to form your own hypothesis later. Just bear with me first. I'm exposing you to what they are. Alternate hypothesis. Okay, so how do we decide which becomes the null, which becomes the alternate? I'm going to teach you that. So first of all, this concern is the concern is this speculating that the modified engine is not going to reduce the emission. Therefore, the mean is going to be greater than or equal to 100. Equal or greater to 100. So thus emission will not go down if the new design is put into production and the sample is misleading. So if we were to go with this, it means that the sample mean of 92 is actually like a very skewed data from the normal distribution. How do I say this in a way that you can understand better? Okay, let's say we have a normal distribution and this is our population mean is 100. So you would mostly get a sample around this value, right? For example, you would get 99.4, 99.6, or 100.1. This one is close to the sample mean, to the population mean. And these are your sample means. First sample mean, second sample mean, third sample mean. Suddenly you get a fourth sample mean that is 92, which is quite far. And you say, oh, this sample mean is actually like, how do I say this? A weird data? That's not a right word to use. A data that is not really, okay, so I have a chat here. So someone is helping me. Anomaly, yes, it's an anomaly. Meaning to say it's not going to be occurring frequently, but somehow that day you got that sample. Correct. Thank you, Haris. So they are trying to say that this 92, this x equals to, this sample mean equals to 92 is an anomaly, meaning to say it's not going to occur that frequent. But today, suddenly we got this sample mean. But trust me, tomorrow you're not going to get it again. So this is what they're trying to say. That this data is wrong, not wrong, anomaly. Anomaly is the right word. So it's a weird data. So is it plausible that this sample of mean 92 could come from a population of mean 100 or more? So the null hypothesis for this guy would be that the population mean, I'm going to write this in math because it's going to be easier to look at, is greater than or equal to 100. So this is going to be our null hypothesis, and the sample mean is lower than this, which is this guy, because of random variation or anomaly from the population mean, whereas our alternate hypothesis is actually less than 100. So I can write it like this. Okay, and the sample mean reflects this fact, which means that the alternate hypothesis is supporting that this sample is good. Okay, thus the sample represents a real difference that can be expected if the new design is put into production. Meaning to say, if I look at this sample, I know that, oh, the car is indeed reduced in gas emission. Okay, so okay, bear with me if you still don't see what null and alternate hypothesis is. Okay, so again, how do we differentiate which becomes the null and which becomes the alternate? So the null hypothesis says that the effect indicated by the sample is due to random variation or the anomaly between the sample and population, whereas the H1 or the alternate hypothesis says that the effect is indicated by the sample, which means that it supports the sample that we get. This is support the assertion, support the Okay, n accurately represents the population. So we always put the null hypothesis on trial. So our trial is this guy. Innocent until proven guilty. So we are going to assume that this is true until we can prove it otherwise. The hypothesis test measures the strength of disagreement between sample and H not or null hypothesis to produce a number between 0 and 1 called the p-value. So this is going to be the key star of hypothesis testing because the p-value tells us whether we reject or accept. Okay, any questions so far? So I have more examples on how to differentiate between H0 and H1 after this. So no questions? Everyone's okay so far? Following me?
Yes, Doctor.
Okay, so does anyone want me to repeat any parts? No? Okay, so I'm going to move on. So the steps in performing hypothesis test, first, you need to define the H0 and H1. Second, you always assume H0 to be true. Innocent until proven guilty. Or true until proven otherwise. Compute a test statistic. A test statistic is the statistic that is used to assess the strength of the evidence against H0, which is the p-value basically. But to get the p-value, we will use the z-score. And we have learned about z-score in a normal distribution. Wait, I need to switch off my WhatsApp. It's bugging me. Okay. So compute the p-value of the test statistic. The p-value is the probability. It is from 0 to 1. Sorry, 0 to 1. Assuming H0 to be true, that the test statistic would have a value whose disagreement with H0 is as great as or greater than actually observed. Okay, just ignore that part first. The p-value is also called the observed significance level. So this is another word for p-value, and I can use this term in the question as well. So you have to know what significance level is, observed significance level. So sometimes I'm going to ask you, what is the observed significance level of this hypothesis test? So you need to know that is also your p-value. Okay. State a conclusion about the strength of the evidence against H0. So this is going to be our conclusion, going to be part of your report as well. Okay, so back to the example just now. So step 2, we are going to assume H0 to be true, compute the null distribution of the sample. So remember our sample mean was 92 and we had a sample standard deviation of, what was it just now? 21, okay, 21 milligram per second. Okay, so since our sample follows the central limit theorem, therefore we have a standard deviation that follows this guy. It can be either the population mean, the population standard deviation divided by the sample size squared, square root of the sample size, or we can use S over square root of N. So we already have S, so we're going to use that 21 over the square root of, what was the value just now? 50. So this is our N. Okay. So why are we calculating this? Because we are going to use the z-score and these values are important for the z-score. So you would get, okay, it's already here, 2.97. Okay, so you have your sample mean, you have your standard deviation sample mean, which is 2.97. And you know that take the assumed value for mu equals to 100 as this is the closest value to H1. Okay, so whenever we're talking about the z-score, okay, the z-score, if you don't remember the equation, it is sample mean minus population mean divided by this guy, if I'm not mistaken. Yes, I think so. Okay, so we already have this. We need to assume this guy. This one we can calculate from S over square root of N or population standard deviation over square root of N. But this one we need to determine from the hypothesis. So our hypothesis talks about mu being greater or equal to 100, or alternate is mu is less than 100. So we know that 100 is like the region, not the region, the point where we are interested in. So we are going to assume that our population mean is 100 based on this hypothesis. So why do we choose mu to become 100? Because if it is 100, how do I say this? It is the closest value to H1 in a sense that if H0 can be any value, right? That is greater than 100. It can be 200, it can be 300, but the closest value to H1 is actually 100, even though it's not exactly H1, but that is the closest value. So in the textbook, they always choose the value that is closest to H1, even though that value is not part of H1, if that makes sense. Okay, so the closest value to H1 would be 100, and we will use that as our assumed population mean to compute the z-score. Okay, so now we can use the z-score, 92 minus 100 divided by 2.97. So our z is going to be, let's look at the solution. Our z is going to be minus 2.69. So again, use your CDF table, and you would find out that minus 2.69 would be, remember that for a normal distribution, your mean is 0. This guy over here is negative. This guy over here is positive. So you know that this is over here. The z is over here. So we are talking about this region, minus 2.69. So the probability that a standard normal random variable z is less than or equal to 2.69 is 0.0036. So this region is 0.0036 probability, right? The total is 1. This region is 0.0036. I'm talking about the region that is equal or less to this value of z. Okay, we got it from the z-score, and this is the probability. Okay, so the probability tells us that this is in percentage, it is 0.36%. So very, very small. So next step is to conclude based on the p-value. So the p-value tells us that if H0 were true, the probability of drawing a sample whose mean was as far from H0 as observed, value of 92, is only 0.0036, which is very, very unlikely. The probability is too small. Therefore, we can reject H0. Okay, so let me recap that in a different way. So when we get a small probability, right? When we get our z-score and we get the probability from the CDF table, and it is super small, what does it tell us? It tells us that the probability of getting a sample mean of 92 from a distribution that has a mean of 100 is 0.0036, which means that the occurrence is very, very unlikely to come from this distribution. Therefore, in another way that you can interpret this is that this is not, the mu is not equal to 100, but a different value. So it cannot come from this distribution, and therefore our mu is something else. So this is what they mean when the probability is too small. If that makes much sense to you. If not, just go with this. Okay, so we reject the H0. So this is the value, sorry, this is the distribution, and 92, the minus 2.69 z-score is over here, and it represents the probability of 0.036, and very, very unlikely to happen. Okay, so if H0 is true, the probability that X takes on a value, yeah, the same thing that I said just now. This is the p-value. Okay, so any questions about this one before I try to further elaborate on this? We're going to do another example. Okay, so everyone's just bearing it. Okay, let's go for it. Next.
Okay.
All right. So these are, okay, let me just recap on statistical hypothesis. So I have a chat here. Doctor, how small is too small? Okay, good question. I forgot to mention that. Reject H naught. So here our 0.036 is super small, and we know that because it's less than 1%. Very, very small, but how small is small? Good question, Haris. So the, how do I say this? Mathematicians, I'm not a mathematician, I'm an engineer. They have agreed on a specific value. I don't know why I'm laughing, but I just find it funny that 5% is the cutoff. And the justification for that is nothing, which is bizarre to me. So the cutoff is 5%. So if I was part of that committee deciding on this, I would have said 3%, and we would have been arguing, right? Because it's totally random. But here they decided that 5% is the way to go. So we'll just follow that because it's already the standard now. Okay, so 5%. I should write that in here because it's not part of the text. P-value is score. P-value. Okay, let me write it here. Reject if less than 5%. Okay, so this is the cutoff. I don't think it's in the notes. I'm gonna check back. Okay, so again, recapping on statistical hypothesis. What time is it? Okay, we have time. A statistical hypothesis is an assertion or conjecture. What is that? Assertion is you are making a statement with full conviction, or you are making a statement that you feel that it is very factual. You believe it to be factual, but we don't know yet, right? So this is like confident lah, confident statement. Right? But don't get this confused with confidence interval, okay? So this is confident as in me being confident, not in the mathematical sense. I don't know how to say that. Confidence statement, I believe so, right? Right. For example, I believe that I am cute. It's a confidence statement. So if there is a conjecture, I think I'm smart. So I'm not really confident that I'm smart, but it's a guess. It's a speculation, just like that. So not too sure. So this is a not too sure statement or like a guess. So your hypothesis testing or your hypothesis question can come from a confidence statement or a guess statement. So both are okay to become your hypothesis questions later on for your project. Okay, so we take a random sample from the population of interest and we use the data contained in the sample to provide evidence that either supports or does not support the hypothesis, like we saw just now. So evidence from the sample that is inconsistent with the stated hypothesis leads to the rejection. So we saw just now that the p-value was super small, which is very inconsistent. If it was consistent, it would give us a large p-value. Therefore, we reject the H naught and we accept the H1 or the alternate hypothesis as plausible. Okay, so these are different scenarios that can be used as hypothesis testing, that can be used as a hypothesis for hypothesis testing. Don't copy this one. A medical researcher may decide on the basis of experimental evidence whether coffee drinking increases the risk of cancer in humans or not. So obviously you can't ask this to your friends. Your friends are not cancer experts. So find a question that your friends can answer. Don't ask them about cancer. We're not doctors here. An engineer might have to decide on the basis of sample data whether there is a difference between the accuracy of two kinds of gauge. For example, you have two equipments, you want to know which one is more precise. So you take the data, right? And then a sociologist might wish to collect appropriate data to enable him or her to decide whether a person's blood type and eye color are independent variables. So they wanted to know if blood and eye color are independent or dependent of each other. That's a weird study, but if it's It's a question, right? Which can be answered. Okay, so continuing, a formal statement of hypothesis is often influenced by the structure of probability conclusion. Let's not, this is like too long. Okay, for instance, if the medical researcher wishes to show strong evidence in the favor of coffee drinking increases the risk of cancer, so they want to support this statement, right? The hypothesis tested should be of the form, there is no increase in cancer risk. Again, you want to support this statement. The medical researcher wants to support with contention that coffee drinking increases the risk of cancer. But to form the null hypothesis, he has to form there is no increase in cancer risk. It has to go against what they want to support, if that makes sense. There is no increase in cancer risk produced by drinking coffee. So you are going to assume this is true until you can prove it otherwise. And then you can say, oh, coffee drinking increases cancer, risk of cancer. Okay, so for example, another example, I want to say that, what would be a good hypothesis? Anyone has a hypothesis question? Okay, I have one. Okay, wait. Maybe this is going to backfire on me. Okay, tak apa. So does the students of ENG3004-6 likes Dr. Nat, for example? So the null hypothesis for this would be they don't like Dr. Nat. That's your null hypothesis. It has to go against what you want to support. Of course, I want to support you guys liking me, right? So the null hypothesis would be my students do not like me, for example. So that's how it has to go against the supporting statement. That's a bad hypothesis. Oh, thank you. Okay, moving on. Okay, so this is where it gets more technical for us to understand hypothesis, and I believe this is the way that we can approach things because engineers like things that are factual. So a null hypothesis H0 is statistical hypothesis that contains statement of equality, such as less than or equal or greater than or and equal. So you have that equal sign here, right? For example, and whereas for alternative hypothesis, you don't have that equal sign. So this is always going to be inequality. Okay, so it's always going to be inequality. So this is one way of approaching your hypothesis testing, is with the signs. Okay, so I want to go over some examples and then we can try to form the hypothesis together. So write the claim as mathematical sentence, state the null and alternate hypothesis, also possible question in the exam. So a university claims that the proportion of its students who graduate in 4 years is 82%. So we know that, okay, let me go back to this. We know that anything that is equal is null hypothesis. Anything that has inequality sign is the alternate hypothesis. That's one way of looking at it. Another way is, if you want to support a statement, your null hypothesis must be of the opposite nature. Okay, so two things. Yes, Amar? Is there any question? No question?
No.
Okay. Because there was like an emoji, but I did not understand. Okay, so university claims that the proportion of its students who graduate in 4 years is 82%. So P equals to 82%. Is this our null or is this our alternate hypothesis? I'll just show you the way to find out. What was it? Is it the null? Is it H0 or H1? Okay, let's go back.
Alternate.
This one. Is it the null or the alternate? P equals to 82%. Null or alternate? So Hari said no. Yes, correct. So just look at the sign here. Easy, right? It's just an equal sign. Therefore, you know it's a null hypothesis. You don't have to think further. So instead of 82%, the right way to write this would be H naught and P is equal to 0.82. So one question you can ask me, but you're not asking me right now, is can we talk about proportion instead of the sample mean? Yes, you can talk about proportion in hypothesis testing. And we will learn about proportion in a bit. Proportion meaning the probability. And the other alternate hypothesis, sorry, not the other. The alternate hypothesis would be, what's the opposite of this? So everyone's just lost. Is not equal to 0.82. This is your alternate hypothesis. Again, you don't have to overthink things. Number 2, a television manufacturer claims that the variance of the life of a certain type of television is less than or equal to 3.5. Variance. So less than or equal to 3.5 variance. Okay, so is this the null or is this the alternate?
Alternate.
Is it? Why is it the alternate? Okay, again, let's go back to the way. If I have any equality sign, it will become null. Even though I said that the null is going to be the opposite of what we want to support, right? But this comes first. This comes first. If you do not have this, then you fall back to the null hypothesis being something that is opposite of what you want to support. Okay, so this is your first step, looking at the signs, because we can't how do I say this? Your mathematical sentence is factual. You can't change that. Okay, so if you have this equality sign, it becomes your null hypothesis. Okay. So what's going to be the alternate hypothesis? Something that is opposite of this, which is 3.5. Okay. And then number 3, wait, I have a chat here. Bukan null ke? Bukan null ke? Betul lah tu. Afika, do you want to say anything? Saya tak faham. Okay, so Afika is not responding. Okay, so okay, let's just continue with this, okay? So if anyone wants to ask me, can ask me later after number 3. So a cereal company claims that the mean weight of the contents of its 20-ounce cereal box is more than 20 ounces. So it claims that the mean weight, so we're going for the mean of the contents of its cereal box is more than 20 ounce. So this is going to be our alternate, and our null is going to be mean less than or equal to 20. Okay, hopefully I got that right. Let's see the solution. So for number 1, it's H naught is P equals to 0.82 and H1 is not equal to 0.82. Number 2, the equality sign is our null, and whatever that does not have the equality sign is your alternate. And the claim that the mean is more can be written as 20. So your 20, it becomes your alternate. Its complement is mu less than or equal to 20. So because it contains a statement of equality, this guy becomes the null hypothesis. Okay, so it's kind of confusing, I admit, but the first thing that we should look at is the signs, and then we go for whatever the statement is talking about. Okay, because that is the technical way to go. Okay, so how much time do we have left? 10 minutes. Okay, let me use another 5 minutes and then we're going to end class. We have another example. Hopefully that can clear things up. In one experiment, 45 steel balls lubricated with purified paraffin. Paraffin is like something like grease, but it's not really grease. Were subjected to a 40 kilogram load at 600 rotation per minute for 60 minutes RPM. The average wear measured by the reduction in diameter was 673.2 micrometer and the standard deviation was 14.9 micrometer. So we have our standard deviation, 14.9. Our sample size is 45. And we have our average. Okay, we're talking about the mean here, which is 673.2. Assume that the specification for a lubricant is that the mean wear, so the specification, the mean wear be less than 675. So the mean wear is less than 675. Find the p-value for testing H0, mu is greater than or equal to 675, and this is the alternate hypothesis. Again, why is it the alternate hypothesis? Because it does not have that equal. This is less. This is less, so this becomes your H1. H0. Okay, so what have we done here? We have formed our null and alternate. Next step is to find out the parameters for our z-score. So we have our n, which means that we can calculate what is our standard deviation sample mean, which is S 14.9 square root of 45. And our sample mean is that 673.2. And our mu that we are going to assume based on our hypothesis is going to be 675. Okay, this is our step number 2. Step number 3, test statistic is our z-score to find the p-value. So that is going to be sample mean minus mu divided by this guy. So this is going to be our z. So x sample mean is 673.2 minus 675. And then this value, I don't know, something. And our z-score is going to be minus 0.81. So it's going to be somewhere around here. And they already given us the distribution for this. And the p-value, which is the CDF that we got from the z-score, is 0.209. If you change that to percentage, it becomes 20.9. That's quite high. Therefore, if H0 is true, there is a 20.9% chance to observe a sample whose disagreement with H0 is at least as great as which that was actually observed. It's just too long. Okay, so let's go back to the question. They were talking about assume that the specification for a lubricant is that the mean wear be less than 675. So they're talking about the mean wear being less than 675 for this 45 steel balls that is lubricated by paraffin with purified paraffin. They're talking about the diameter of the ball after being purified. So the hypothesis, the null hypothesis that we assume to be true was this guy. We always assume the null hypothesis to be true until we prove it otherwise. So we are assuming that the ball did not reduce in diameter. The specification for a lubricant is that the mean wear be less than 675. So we are forming a null hypothesis that is going against this, right? It's going against this statement. So going against this statement, we found out that the percentage is 20.9. So there is 20.9 chance to observe a sample whose disagreement with H0 is as least as great. I need to stop saying this sentence. Since 0.209 is not a very small probability, we do not reject H0. Okay, so we conclude that H0 is plausible. The data does not show conclusively that the lubricant meets the specification, which means that our alternate hypothesis cannot be supported. Note that we are not concluding that H0 is true, only that it is plausible. We're not saying that it is 100% true. We're saying that it is a possible statement. After all that, is still not true, right? What effort. So again, you have to have this kind of statement in your report later on. We're going to continue learning about hypothesis testing, and hopefully you can progress along your report as we learn. Okay, so any questions, feel free to ask me. Otherwise, have a great rest of the day. I'll see you next week. Bye-bye, guys.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Bye.